For today, we're going to be working on lesson 3.5, which is on defining or performing some basic matrix operations. So this is lesson 3.5 from your text. Lesson 3.5, as I said, starts to define some of the basics of what is a matrix. All right, and so we're going to be using this idea of a matrice. A matrice or a matrix, matrices if we're talking plural, matrix if we're talking about a single. A matrix is a rectangular arrangement of numbers in rows and columns. We typically use these braces, these kind of square brackets, to represent a matrix. And in that matrix, we can have a series of numbers, and I'll just use like A, B, C, D, E, F, something like this. We can have a series of numbers in that matrix. And again, those entries or these numbers in the matrix are what we refer to as elements. All right? Now, when we dimension a matrix, when we talk about the dimensions of a matrix, we always talk about the rows by columns. And so, for example, this one has 2 rows and 1, 2, 3 columns. So this would be a 2 by 3 matrix. All right? So again, the matrix is the rectangular array of those, rectangular arrangement of those numbers. The dimensions of that is always listed as rows by columns. And then the elements are the numbers or the elements inside of those various spots. So, for example, if I said first row, second column, that happens to be the letter B, or the variable B in this case. All right? Now, equal matrices are those matrices that are, well, as you can imagine, equal. So they have the exact same dimensions, they have the exact same elements, they are same elements in corresponding positions. So, for example, the matrix 4, 2, 3, and 7 is equal to the matrix 4, 2, 3, and 7. No other matrix is equal to that one besides 4, 2, 3, 7. Now again, we can put some various variables and things like that in there. But for the most part, just assume that, again, if two matrices are equal, if they are in fact equal, then this has to be equal to this. So basically you're getting 4 equations. You're getting 4 is equal to 4, 2 is equal to 2, 3 is equal to 3, and 7 is equal to 7. About the most boring 4 equations you're going to get, but again, each element matches its corresponding part in the other matrix. All right? A scalar is a real number by which you can multiply a matrix. Okay? And we'll do an example of a scalar multiplication here shortly, but again, a scalar is something when we multiply a number by an entire matrix, that number that we're multiplying by is called a scalar. And finally, as we just got done talking about scalar multiplication is the process of multiplying each element in a matrix by a scalar. So for example, maybe we got 2 times the matrix 1, 5, negative 3, 8, negative 4, and 7. And so here shortly we'll talk about how to multiply that scalar, which happens to be 2, by the entire matrix. Okay, so as we start talking about adding and subtracting matrices, when we add and subtract matrices, basically what we do is we add or subtract corresponding elements. Okay, we add or subtract corresponding elements. You can add or subtract matrices only if they have the exact same dimensions. So that kind of makes sense because if we're going to add these corresponding places, you have to have a first row, first column. So A plus E is going to be equal to that first entry in the new matrix. B plus F is going to be equal to this entry here, which is B plus F, and so on and so forth. Subtracting the same way. A minus E is A minus E. And so the first row, first column will be the result of subtracting first row, first column from first row, first column. And so on and so forth. First row, second column, first row, second column is B take away F, and so that's where they get B take away F. All right, so let's go ahead and let's give this a shot. Let's try a couple of examples here. Top of the next page then, we want to add and subtract matrices. And so if we're looking at letter A here, we're going to say go ahead and subtract these 2. Now right off the bat you can see that this is not possible because I can do 6 take away 3, but I can't do negative 2 take away, there's nothing here, right? So if I want to subtract these 2, these both have to be 2 by 2 matrices. If they're not, we can't subtract them. All right? So it says the dimensions of this matrix, 6, negative 2, 1, and 3, are 2 by 2. Again, 2 rows, 2 columns. However, the dimensions of this matrix, 3, 2, is 2 rows by 1 column. So it's 2 by 1. So you cannot subtract the matrices because they don't have the same dimensions. Okay, the dimensions of these, the dimensions are equal. The dimensions are the same. So because in the next example the dimensions match, this is 3 rows by 2 columns. This is a 3 by 2 matrix. This is 3 rows by 2 columns. So this is also a 3 by 2 matrix. So because the dimensions match, they're both 3 by 2s, we can go ahead and we can add, again we're adding, we can add entries that match. So let's do with one color here. Let's go ahead and try this. Let's say negative 2, let's do it down here. Negative 2 plus 1. And negative 2 plus 1, as you can imagine, is, we're going to write negative 2 plus 1. And negative 2 plus 1 is negative 1. And so the first entry in my new matrix is going to be negative 1. All right? Now what we're going to do is we're going to switch gears a little bit. Now we're going to take a look at this. This is 1 plus negative 4. And so we're going to write that in here. This is 1 plus negative 4. And as you know, 1 plus negative 4 is negative 3. All right, let's go again. Let's pick a different color again. Now we have 0 plus negative 2. And again, we're doing now second row, first column, second row, first column. So 0 plus negative 2, 0 plus negative 2, and that is negative 2. Continuing on that pace, we'll go ahead and choose a different color again. This is now 3 plus 9. And so 3 plus 9 is 12. And then we'll just go ahead and finish this last line. This is 7 plus 1, 7 plus 1, which is 8. And 6 plus 5, which is 6 plus 5, or 11. All right. Now I realize that's a little sloppy and a little hard to read, but generally speaking, basically all you have to do is just find the corresponding elements and add them together because we are adding. All right. Now let's talk a little bit about that idea of a scalar multiplication. Going back to this idea of a scalar, we want to multiply a scalar. So all that means is this is like the extended, this is the distributive property on steroids. The distributive property says if I have 3 times x plus 2, that means that both of these get multiplied by 3, so this is 3x plus 6. A scalar multiplication looks kind of like that. It is, like I said, the distributive property on steroids. So everybody in here gets multiplied by a 3. So this is 3 times 0. This is 3 times 2. This is 3 times negative 7. This is 3 times negative 1. And I'll use these now. 3 times 6. And 3 times 4. So 3 times 0 is 0, 3 times 2 is 6, 3 times negative 7 is negative 21, 3 times negative 1 is negative 3, 3 times 6 is 18, and 3 times 4 is 12. And so that's multiplying by a scalar. All right. In the next example, we're multiplying through by negative 2. So just like before, again, if we were distributing a negative, we'd distribute the negative with it. This is negative 2 times 1. This is negative 2 times 0. This is negative 2 times 3. And this is negative 2 times negative 5. Now the last one's really the only one you got to be careful with because negative 2 times 1 is negative 2. Negative 2 times 0 is 0. Negative 2 times 3 is negative 6. And then be careful with this. Negative times a negative is positive, so this should be positive 10. All right, so our result matrix is negative 2, 0, negative 6, and 10. So I want you to pause your video. I want you to try the next two. You're going to be doing a subtraction, and then you're going to be doing a scalar multiplication. Go ahead and give that a shot, and then restart your video, and we'll check your solutions. All right, so for the first example, we're doing a subtraction. Now, there's a couple different ways to do this. We can think about this subtraction as simply, we're going to just put our result over here. This is negative 6, take away 3. So negative 6, take away 3. This is 2, take away 0. 2, take away 0. Negative 1, take away 7. Negative 1, take away 7. And then finally, negative 5, take away negative 1. Negative 5, take away negative 1. Careful, there's a lot of negatives there, right? So then we're going to go ahead and we're going to simplify. Negative 6, take away 3 is negative 9. 2, take away 0 is 2. Negative 1, take away 7 is negative 8. And then finally, negative 5 minus a minus 1 becomes negative 5 plus 1, which is negative 4. Now the other way we can think about that is we can think about that as the distributive property, kind of like multiplying through by a scalar. We can think about really making this plus a -1 times this whole thing. And so we can take a -1 and sort of distribute that, again, using a scalar multiplication to everything in the second matrix. So this is -6 to -1, -5. And now we're adding -3, 0, -7, and +1. Because again, if we multiply every one of those by -1 in the second matrix, we simply change all their signs. Now we add. -6 plus -3 is -9. 2 plus 0 is 2. -1 plus -7 is -8. And -5 plus 1 is -4. Whichever method you like better there, I say go for it. Again, this is scalar multiplication, so every single term in here gets multiplied by -3. And so this is -3 times -1, and I'll just run through the numbers real quick. We should have 3, -9, +6, -12, -6, -27, +18, -3 times 0 is 0. All right, so those are our two practice problems. So let's then go ahead and talk about properties of matrix operations. Effectively what we have here is we have that A, B, and C are matrices with the exact same dimensions because they have to have the same dimensions to add them. So for that purpose, we're going to say that we're going to they have to have the same they have to have the same dimensions. K is some random scalar, which we'll get to in just a second. The associative property of addition for regular numbers, like for example 2 plus 3 plus 5. 2 plus 3, then plus 5 is the same thing as 2 plus 3 plus 5 grouped this way. This is called the associative property. And so the associative property works for matrices as well. This is the same thing as A plus B plus C, which effectively says when you add matrices, you can group them and add them, you can group them in any order you want to. All right, so we can either add the first two together and then add the third, or we can add the second two together and add the first. However you choose to do it is fine. The commutative property of addition says that A plus B is the same thing as B plus A. All right, again, just like 2 plus 3 is the same thing as 3 plus 2. That's the commutative property of addition, and so commutativity also applies to matrices. The distributive property of addition, just like we know that we already talked about this, 3 times x plus 5 is the same thing as 3x plus 15 because we get to do this. So true is it for matrices. This is K times matrix A plus K times matrix B. So you could first add the matrices together and then multiply by the scalar, or you can distribute the scalar and multiply each one of them by the scalar. And again, the distributive property also works over subtraction. This is Ka minus Kb. All right, so let's take a look at a story problem here. It says 2 pet stores sell cats and dogs. Sales from each store last month and this month are shown below. Last month, store 1 sold 42 dogs, 33 cats. Store 2 sold 56 dogs and 21 cats. So we're going to organize that data for last month. We're going to organize the data for last month into last month matrix, and we're going to call that matrix A. And so the store is going to be the row, and the column is going to be the number of dogs and cats. So for store 1, we should have 42 dogs, 33 cats. So 42 and 33. For store 2, they sold 56 dogs and 21 cats. This month, store number 1 sold 36 dogs and 51 cats. And over here we have 48 and we have 37. All right. It says write a matrix for the average monthly sales by adding A and B and then multiplying by 1/2. Again, if we're trying to find the average, we could do this as 4 separate problems. We could take the average for store 1 for dogs, we could take the average for cats, the average for dogs, the average for cats, and do that 4 times. We can really do this in a scalar using matrices. So matrix 1 is 42, 33, 56, and 21. Matrix B is 36, 51, 48, and 37. Now, because we know all of the elements here, just like, for example, 3 times 2 plus 4, we wouldn't distribute this because we'd simply add 2 plus 4. The same goes with this addition of these matrices. This is going to be 42 plus 36, okay, and 42 plus 36 is going to come out to 78. So this is 78. And when I add the next 2 entries, 33 and 51 comes out to 84. And when I add the next two entries, I get 104. And when I add the next two, I get 58. So again, we add each entry, first row, first column, first row, first column, first row, second column, and go on from there. Now, we're going to take half of those because, again, the average says add them together and divide by 2, so we're just going to take half by using a scalar multiplication. And half of 78 comes out to 39. Half of 84 comes out to 42. Half of 56, or I'm sorry, half of 104 is 52. And half of 58 is 29. And so now, again, for the two stores, again, this is still store 1, this is still store 2, this is still dogs, and this is still cats. So for store number 1, they sold 39 dogs, 42 cats, while store number 2 averaged 52 dogs and 29 cats. So we can use matrices to help us organize some of this information. So in example 4 now, we're going to solve a matrix equation. And we just got done saying that, listen, we know that the sum of these two, when I add these two together and multiply by 4, essentially 4 times 3x plus 1 has got to be equal to negative 8. Now, I don't really like this, so I'm going to kind of do it over here on my own. So I would ignore that right now. I just, again, if I look at this entry, okay, 1 minus 2, well that's, I'm sorry, 1 minus 3, that's negative 2, and 4 times negative 2 becomes negative 8, which we already know that, right? 0 plus 2 is 2, and then 4 times 2 is 8. We don't care about those two entries because there are no variables there. But for the first row, first column, there's a 3x and a 1, and so we're going to take that first row, first column, and we are going to highlight that. We're talking about here, and here, and here, here. All right? And so according to matrix multiplication, the scalar and the addition, we've got 4 times the quantity, 3x plus 1. And so I'm going to write an equation, 4 times 3x plus 1. Because if I add the first row, first entry with first row, first entry, or first row, first column in both matrices and then multiply by 4, I get negative 8. Now simply distribute. This is 12x plus 4 is equal to negative 8. Take away 4 from both sides, I get 12x is equal to negative 12. And so x equals negative 1. On the other side then, we're interested in these numbers in the bottom right-hand corner. So those numbers in the bottom right-hand corner, 6, negative 2y, and 0. And don't forget the 4 out in front. So this becomes 4 times the quantity 6 plus negative 2y, or 6 take away 2y, is equal to 0. Whichever way you want to do it, again, it's 6 plus negative 2y. All right, so we can distribute here. This becomes 24 minus 8y is equal to 0. Take away 24 from both sides, because again, we are solving for the negative 8y. And divide both sides by negative 8. You get y equals positive 3. All right? So effectively, this equation right here should be in this place in your notebook, and this equation here should be in this place in your notebook. We had to write a little bit bigger, so. All right, so let's go ahead and try a checkpoint problem and see how this goes for you, and we'll be right back with your solution for this particular problem. All right, in our checkpoint problem, we are concerning ourselves with this entry because there's an x. So we've got negative 2, the negative 2x, and then because it's first row, second column, we want this one here and that one there. So we find that corresponding spot in all 3 entries. Okay, we find that corresponding spot in all 3 entries. And so according to that now, it's negative 2 times negative 2x minus negative 6. Again, you've got minus a minus here, so you've got to make sure you're real careful with that. Equals 12. Now, minus a minus, we already said that turns into a plus. And so this is really just a big old plus right here. Now go ahead and distribute. Positive 4x, because negative 2 times negative 2x is positive 4x. And negative 2 times 6 becomes negative 12 is equal to positive 12. To get rid of negative 12, we're going to add it to both sides. 4x is equal to 24, and so x is equal to 6. Once we have that entry, now we're going to go ahead and we're going to take a look at the other place where we have a variable, which looks like right here. So that is second row, first column. So second row, first column, second row, first column, second row, first column. And now we're going to go ahead and we're going to make an equation for that. So this is now -2, because again, the leading coefficient here is -2 times 1 minus -5y. Again, don't forget, this is a subtraction sign. So it's 1 take away -5y. And all of that's supposed to be equal to 8. Once again, simplify your signs. Minus a minus is a big old plus. Distribute. This is -2 minus 10y is equal to +8. From there, we're going to add 2 to both sides. -10y is equal to +10, and you get y equals -1. So those are the values of x and y. And that concludes our lesson.